Okay, so let us try this problem. We have here a simply supported beam having this loading. We have a couple here, a pointed load here, and then a varying load, which is a second degree one. So in dealing with this type of problem, we need to recall the principle of the area and the centroid of this if we have a second degree curve. So the general formula, we have the general formula for a spandrel that having a base and a height. Of course, nth degree here could be a straight line or any degree. The area is just equal to 1 all over n plus 1 base times height. And the centroid is located, measured from the height, that is in terms of x bar, that is 1 over n plus 2 of the base. Okay, so if testing this formula in a straight line, it will just, this spandrel is in the form of triangle, right? And then if that straight line is 1, or n for straight line is first degree, then the area for a triangle is 1 all over 1 plus 1, or 1 half base times height. It will yield to the formula of the triangle, and then x bar as well. So if n is 1, then we have here 1/3 of the base, which is actually the location of the centroid of the triangle. So anyway, this is the general formula you need to remember. So on this formula, of course, if this is the spandrel, okay, if we have a straight line, we have an equal or 50% of this rectangle. Actually, if we have a straight line, so this is 50%, and that is 50%. So in terms of a curving line between these 2 points, if we have a second degree, of course, this area here would now become 1/3. Okay, so if we have a second degree, applying this formula, we have 1/3 base times height. Of course, the remaining here is 2/3 base times height. So therefore, if you're dealing with a curve that is like this, having a curve like this, the thinner one is 1/3, and the bulky area under this is 2/3 base times height, and so on and so forth. If you deal with the third, you will apply also this principle, wherein, of course, if you have a third degree, this will have a more smoother curve here, wherein this now becomes 1/4 of the base times height, and the remaining is, of course, 3/4 base times height. So what I'm trying to point out is, if we deal with the thinner side of the area, that is 1/3, and the thicker side of the area is 2/3. Okay, so these are the principles that we need to remember in dealing with this type of spandrel. Now, ratio and proportion can always be applied here on the spandrel, whether it is a first degree or a second degree or a curve. Okay, so to give you an idea on that ratio and proportion, of course, if we have here a triangle. You just have to ratio and proportion the base and the height. And if we have here a curve, okay, whatever is the degree, for example, we have a second degree curve, okay. Remember that this is a first degree curve if we have a straight line, and from second degree onwards it will become a curved line, okay. So recalling your analytic geometry, if we have a squared variable, that simply means that the axis is curving, like for example, if we have a straight line x and y here, recall that the formula for parabola or the second degree curve is either x squared is equal to 4ay, okay, or it may be y squared is equal to 4ax. Of course, this has these two is different in terms of the curving of the curve. So if this is the equation, we can see here that the squared variable is x, meaning this expression is either bending the x, okay. So if we have a positive value here, or this particular equation is a curve bending, okay, upwards. And if we have an x squared negative 4ay, that is bending downwards, meaning these two equations here, this one and this one, will have just two scenarios. It is either concaving upwards and concaving downwards. Why is that? Because the variable here that is being squared is x, so meaning just bend the x, okay. When it is positive, bend it upwards, and when it is negative, bend it downwards. So that is the rationale here. How about y squared is equal to 4ax? Now this time the variable squared is on y. That is why the bending on this equation is either rightwards, concaving rightwards, or concaving leftwards, okay. So that is your analytic geometry. So for this particular equation, y squared is equal to 4ax, that is concaving rightwards, okay. And if we have y squared is equal to negative 4ax, this is actually concaving leftwards. So that is the scenario here. So if you are going to use ratio and proportion now, say for example, if we have a second degree curve, if you wish to have a ratio and proportion out of this, say I'll just have a concrete dimension here. Say if we have a dimension equal to 5 and this is 2 or 3, if we wish to have a ratio and proportion for this smaller spandrel, say this is y and that is x, we can just say that y is to x squared, okay, is equal to 5 is to 3 squared. Notice that your horizontal lines here were squared. Why? Because of this concept, okay. So your curve is bending towards up. It is an indication that your x is bending, and if x is bending, therefore just squared all the x's, okay. So if your curve is happen to be 3 degrees or the third degree, Then you just have to adjust that one. Y is to x cubed is equal to 5 is to 3 cubed. Okay, so that is how to do ratio and proportion in a triangle, of course, or spandrel. Of course, if you have a triangle here, say 5, 3, and then this is x and y, we'll just have to say that um, 5 is to x, of course, raised to 1. That is a first degree because this is a first degree. And this is um, say this is x and this is y. Okay, 5 is to x as to, sorry, 5 is to y as to 3 is to x. Okay, so what are the x's here? X and 3. So it is understood that this r is to 1 because this is a first degree curve for a triangle. It is simply straight line. Okay, so that is for our discussion. Going back to this problem, of course, we remember this in order for us to use ratio and proportion if we wish to have a graphical method. And then we place now the reaction. So solving for the reaction, we need to, of course, reflect the forces here. First and foremost, we have here the spandrel, second degree spandrel. Of course, when we have a second degree, we have 1/3 because 1 over n, or 2 plus 1, that is 1/3 base times height. So all of this is 18 by the height 36. So we have 216 for this resultant that is located, measured from the height, that is 1 over 2 plus 2 over 18, or 18 all over 4, that is 4.5 meters. So knowing all of that, we can easily perform summation moments at B. Okay, so we have a counterclockwise 216 times 4.5. Okay, and then the pointed load at this portion, we have negative 200 times 6. Okay, this one. And then this clockwise 480, and then plus 18 times RA. We will have an answer of reaction at A equivalent to 94 Newton. So we use also another moment, the other support. We have 480 plus 200 clockwise times 7.5 times 4 plus 4.5, that is moment arm of 12. And then of course this is 216 times the moment arm from A up to this point is 18 minus 4.5, that is 13.5. And then we less the counterclockwise RB times the moment arm 18. So we perform this equation and come up with RB 322 Newton. Okay, so we check this. So checking that one will yield to 0. Okay, so we check that by having the equilibrium equation along the y-axis. Okay, so we have yielded to 0 is equal to 0. Okay, so we're going to place now the reaction here. We have 92 and 322. Next, we go section per segment. So we first set x to segment. Say this is segment 1. Okay, I'll just set that as segment 1. We have the 92, and then we have 1/3 x times y. Okay, so this is where we are going to have now a ratio and proportion to relate x, or to express y in terms of x. First, we have the larger spandrel that is having a height of 36, and then the base is squared here because, as we all know, that is curving, wherein x is bended upwards. Then for this smaller spandrel, we just have this y is to x squared. So solving for y, we have cross multiplication 36 x squared all over 18 squared, and that is 0.11 x squared. So first we have an upwards 92 minus 1/3 x times y. This is 0.11 x squared. Hence we have this, the simplified term for this. So this is our equation for segment 1, shear equation. For moment equation, we have, first we have 92x minus 0.037 x cubed times moment arm of x all over 4. So therefore mx is 9.25 times 10 raised to negative 3x raised to 4. So this will be our equations, Vx and Mx. For segment 2, so x is extended along this boundary between 4.5 and the end of 7.5. Say that is segment 2. So perhaps we can just update our first equation, since the first equation have a similar cut or slice. However, it will only include here, or the variation includes this 480 Newton meter there. I think we'll just maintain this one because there is no update so far in Vx. Okay. And then for Mx, we'll just copy that one. Okay, and then we add that 480. So we have this as our equation. And then for segment 3, we'll just have to extend this x, extending it from the boundary between the start of 7.5 and 6. So as an update, the variation on the second segment is just additional 200 here, which will affect our shear equation but not our moment equation. So let us note, this is just to be copied and then just add here or subtract 200. Okay, so copy and then subtract the 200. Then mx is maintained, but we need also to add the effect of this 200, and that is 200 times moment arm. What will be the moment arm of 200 if this is to be cut at that portion? So this is a variable from the end of 7.5. So meaning 7.5 plus 4.5 is 12. So therefore, the remaining distance here is x minus 12. So that is placed there. Okay, so therefore we will be having now our equation Vx and Mx. So this equation covers all we need in the beam span. So in the meantime, let us do this by graphical method in order to come up with the shear and moment diagram, aside from assigning values of x's here. Okay, so we draw the shear line here. First, starting at A, there will be a 92 going up, 92, and then we less this spandrel area. What is that spandrel area equal to? So if we illustrate that, we have here of 4.5 spandrel area. Of course, just the same, we express this by y. So therefore, it is just but and proper to, of course, refer to the equation, because again, we will refer to an equation involving proportioning of y, which we have already done in our equation. So the segment 1 equation is this one, 92 minus 0.037 x cubed. We have, when x is 4.5, Vx is 88.63. So we'll just place it here. And I think we should continue up to 200. Why? Because we do not have to terminate at this point, because 480 couple has no effect on the shear diagram actually. So anyway, we just reflect this for a while. Vx is equal to 88.63 when x is 4.5. Okay, anyway, we do not need that value. So we will proceed directly on 200. Okay, so using the segment 2 equation. So here's the segment 2 equation. For Vx, we have 92 minus 0.037 x cubed. Oh, actually, we have the same equation between this segment 1 and segment 2. So we'll just say that when x is 12, our Vx is 28.06. So I think it should be greater than this. Okay. So as we increasing x, this shall go down. And then of course, on this, we have to reduce it 200 units downwards. So 28.06 minus 200. We have negative 171.94. And of course, we wanted to move on to the 18th distance here, or the last segment. By the way, this is 322. So all we have to do is to substitute from segment 3 a distance of 18. So we can say that here, segment 3, when x is 18, Vx is negative 322. Okay, so negative 322. So it will further go down. Okay, and then it will turn back to 0 here because of this reaction. Okay, so let us connect first the lines here. Okay, so what about the connection between these two? So investigate the load diagram here. This is increasing. So if it is increasing, it should have a downward concave curve. So here it is. And then for this, it is also connected by a downward curve. Okay. So the degree of curve is a third degree curve, since we have here a second degree curve for our given loading. So finally, for our moment, we will have a consideration on this transition. So we do not have any transition here. It is just on the 12th location. So the point where the line crosses the shear 0 is at this point actually, okay, at this segment. So we do not need any calculation to locate this, because this is already defined by its distance, that is equivalent to 12. So all we need is to substitute 12 in our equation of segment number 2. Okay, where is that? So here it is. So we'll just have when x is equal to 12, the maximum moment is equal to 1392.19. Okay, so this is the maximum moment. So we illustrate that in our moment diagram. Say that is m and that is 0. We'll just indicate here the value. Okay, so to connect the tree here, because starting at this point, of course we need to terminate where there is couple. Why we terminate where there is couple? It is similar to a point load where it affects our diagram, especially in the moment. So 480 here has no effect in our shear diagram. However, it is affecting our moment diagram. So there will be some addition on the coordinate along this section. Okay, along this section where 480 is applied. So we're going to derive our coordinate first from A up to the end of 4.5. That is using the equation from segment 1. So from segment 1, so I think this is the equation. We will just say that when x is 4.5, the value of mx is equal to 410.206. Okay, so we're going to place it here. 410.206. So here it is at this point. Okay, 0 to 4.5, we reflect 410.206. Okay, that's the 410.206. Then we consider this positive 480 here. So 410.206 plus 480, we have 890.206. Okay, so eventually your equation will put up this maximum moment up to 0 when we check that one in our equation from segment 3. Just substitute here 18 and it will yield back to 0. Okay, so to connect these lines from 0 to 410, take note that we have here a decreasing curve, a decreasing manner. We have a concave downward connection. So here it is, and then an increase, just a straight line. So that your straight line is that one, and then of course the same concave downward curve to connect this. Okay, and then it will yield back to 0. Okay, so this will now be our moment diagram for this particular problem. Okay, so I hope that helps, and then next you should your next step should be practice solving shear and moment diagram. So thank you.